We looked at solving exponential equations when they had a common base. We don't always have common bases though, and so we need to use another technique. This technique involves using logs. Now we can use logs like an operation. What I mean by operation is multiplication, division, subtraction. We can use log like an operation and undo to the x. So that will be our opposite operation. And we'll see what that looks like in just a second. Let's do an example. That's the best way to understand what this means. Say we have 4 to the x equals 64. Now, I want to go ahead and do this using common bases first so that we have a good idea. We can check our solutions after we use logs. This is 4 to the x equals 4 cubed. So by common bases, we know that x equals 3. Now let's solve this problem using logs and see what we end up with. So let's do 4 to the x equals 64. Since we have to the x, we need to undo to the x. We need to get x out of the exponent. And to do that, we use our log operation, so we take the log of both sides, which means we have the log of 4 to the x equals the log of 64. Now we're going to use our properties of logs to simplify this. Properties of log says I can move that x. So I get x times the log of 4 equals the log of 64. Notice that I just took the common base, the log base 10 of both sides. You can take the log base anything. I just like doing 10. It's the easiest one to do, and I'll convert later on. So x times the log of 4. The log of 4, you could type it in your calculator right now. The log of 4 is just a number. So I can go ahead and divide by the log of 4. And I'm going to divide both sides by the log of 4. So I have x equals the log of 64 over the log of 4. Now, we learned a property about changing bases. So we could rewrite this as the log base 4 of 64. Now, if this is possible, we want to simplify it further. If it's not possible, we leave our answer in log form. So what is the power that makes 4 64? It is possible. X equals 3. Matches what we got earlier. So when we take the log of both sides, we're just using an operation that undoes raising something to the power of x. Now this one was kind of nice because we could solve it using common bases. Let's look at some examples where we don't have common bases. 7 to the x equals 9. There's no way you can write 7 and 9 with a common base. So to solve this, I'm going to take the log of both sides. And I'm just going to take the common log of both sides. In a little bit, I'll show you taking another type of log of both sides. You're going to see it doesn't make a difference. So when we take the log of both sides, we have the log of 7 to the x equals the log of 9. Now we can use our properties. So we have x times the log of 7 equals the log of 9. Now remember, the log of 7 is just a number, so we're just going to divide by the log of 7. So we end up with x equals, those cancel, the log of 9 over the log of 7. If I wanted to get my answer in decimal form, I could go ahead and type these two things into my calculator right now and find them, because calculators know how to do common logs. But I'm probably just going to leave it in log form. So I'm going to use my common base property that says that I can write this as the log base 7 of 9. I don't know what the power that makes 7 equal to 9, but there is such a number. It's a crazy decimal, so that's why I chose to leave my answer like this. The solution to the equation 7 to the x equals 9 is the log base 7 of 9, the power that makes 7 into 9. Kind of makes sense when you think about it. This one's a little bit more exciting. This time we have 5 minus x in the exponent. Still okay though. Since we have our exponentials already isolated, it's just 10 to the something, we can go ahead and solve by taking the log of both sides. I'm just going to take the log, the common log of both sides. Now I'm going to use my property, and I'm going to bring down 5 minus x. Now, we want to solve for x, so we need to get it out of the parentheses. So I'm going to need to distribute the log of 10. I'm going to distribute it, and then I hope some of you guys have noticed something. We'll talk about that after I distribute it. 5 times the log of 10 minus x times the log of 10 equals the log of 8. 5 times the log of 10 is just a number, and negative x times the log of 10 is x times a number. So we would need to subtract from both sides and divide. However, I took the common log of both sides. What is the log base 10 of 10? It's 1. So conveniently enough, this is 5 times 1 minus x times 1, which equals the log of 8. Well, all right, so that means this is 5 minus x equals the log of 8. Minus 5 from both sides, so we get negative x equals the log of 8 minus 5. Divide both sides by negative 1. You get x equals negative log of 8 plus 5. And we're done. That was pretty convenient for us. Usually that doesn't happen and you have a bunch of logs in your answer. We could have saved simplifying until the very end, but we lucked out and we were able to simplify earlier. If we didn't know our properties of logs or how to evaluate logs, we wouldn't have been able to simplify it like we did. Remember though, that the negative log of 8 plus 5 is just a number. Type it into your calculator if you want to see. So it's okay that we're leaving our answer in this form. It's actually the most precise form because logs are irrational. Or most of them are. 2 to the 3x and 30. Can you write either of those with a common base? It'd be really nice if we could, then we wouldn't have to take the log both sides. But unfortunately, we have to do it. Again, I'm going to take the common log of both sides. Then I'm going to employ my properties. Now, we need to get x by itself, so we're going to have to divide. We're going to have to divide twice, or once, but by two things. Just to make it really clear what I'm doing, I'm going to divide first just by the log of 2. That means I'm left with 3x equals the log of 30 over the log of 2. We can divide by 3 now, or we can change bases now. I'm going to change bases. Using the change base rule, I can say that this is the log base 2 of 30. And now I can divide both sides of the equation by 3. So I can say that x equals 1/3 times the log base 2 of 30. I could say the log base 2 of 30 divided by 3 as well. I just think it looks nicer with that nice little 1/3 in front. This one's a little bit different. We don't just have an exponential. We have a 3 times an exponential. So before we can take the log of both sides, we're going to have to get rid of that 3. We're going to have to divide. So when we divide both sides by 3, we're going to end up with 2 to the x plus 4 equals 15. Now our exponential is alone, so we can take the log of both sides. So we have the log of 2 to the x plus 4 equals the log of 15. I'm going to move that x plus 4 in front. I'm going to put it in parentheses. The log of 2 equals the log of 15. Now, we could distribute if we wanted to, or we could divide by the log of 2 if we wanted to as well. I'm going to show you a few different methods. You can decide what works best for you. If we divide both sides by the log of 2, we end up with x plus 4 equals, I'm going to use change base right away, the log base 2 of 15. Now we just need to subtract, so that was pretty smart of me not to distribute. So we have x equals the log base 2 of 15 minus 4. So, could have distributed, I would have ended up with the same solution. It's just that, see how knowing your algebra helps things go a little bit easier? It's a problem-solving technique. It's a way to make solving easier. So 14 equals e to the 2x plus 1. This is still an exponential problem. This one just happens to deal with the natural base of e. Well, let's go ahead and first isolate our exponential just like we did in the last problem. Except in this case, we just need to subtract. So we end up with 13 equals e to the 2x. Now here's where we can take the log of both sides. I did tell you that I don't always take the common log, and the only time I don't take the common log of both sides is when I have e as my base, because it makes more sense to take the natural log of both sides. You'll see why in just a second. So I'm going to take the natural log of 13 and the natural log of e to the 2x. We're going to see a lot of these types of problems when we look at applications. Newton's law of cooling uses the common base as well as some other chemical and biological data collection things that will make sense when we start looking in more depth at applications. Alright, so let's use our properties. Properties say that the natural log of 13 equals 2x times the natural log of e. Here's where we see why I took the natural log of both sides. Natural log of e is the log base e of e. What is the power that makes e e? It's 1. So essentially that one goes away because I have 2x equals 1, or 2x times 1. Divide both sides by 2. And we can say that our answer is x equals the natural log of 13 over 2, or 1/2 times the natural log of 13. Again, that's just a number. It's something your calculator could do for you if you really wanted to know that crazy, never-ending decimal. This is the most succinct way to write it and the most precise. So, again, the only reason I took the natural log of both sides was because we were dealing with the natural base. So in this one, I need to isolate my exponentials again. So we have 2 to the 4y plus 1 equals 3 to the y. Now I'm ready to take the log of both sides. I know I have to take the log of both sides because I can't do a common base. So the log of 2 to the 4y plus 1 equals the log of 3 to the y. Now we can go ahead and use our properties. So 4y plus 1 times the log of 2 equals y times the log of 3. Now we need to get y out of those parentheses, so I'm going to distribute. This is a place where you could probably do a couple different solving methods. This is the method I'm going to use because it helps me organize what's going on. Now we have y on both sides still. I want to get all my y terms together, so I'm going to subtract the 4y log 2. So we end up with the log of 2 equals y times the log of 3 minus 4y times the log of 2. Now we get to do an awesome thing, which is factor. They both have a y term, so let's factor out the y. That's the GCF. So y times the log of 3 minus 4 times the log of 2 equals the log of 2. Now I know you're going, oh my god, this is so gross and nasty. But the log of 3 and minus 4 log of 2, it's just a number. You could type it in your calculator and get that gross decimal. But because we want the exact answer, I'm leaving it in log form right now. It's just a matter of dividing at this point. I'm going to divide both sides by the log of 3 minus 4 log of 2. So I'm going to write my final answer up in the corner because I'm running out of space. So y equals the log of 2 divided by log of 3 minus 4 times the log of 2. And we could figure out what that decimal approximation was if we wanted to, type it all into the calculator. But I'm going to leave it as it is because I want to have the exact answer. So solving exponentials where we don't have a common base is a little more complicated because we need to take the log of both sides. You can take whatever log you want. I usually take the common log unless I'm dealing with e, and then I would take the natural log of both sides. There's a lot more examples as well as some other places for resources on our Canvas page about solving exponentials using logs.